Hello class. This video we're gonna go ahead and finish up the section on how to graph polynomial functions. So as you remember from part one, we went ahead and described what makes a polynomial function, how to write it in standard form, and how to identify some of the parts. So if you remember, the definition of a polynomial function is the most important part of it was that all the exponents are whole numbers. Whole numbers meaning, remember whole numbers, whole numbers are numbers like 0, 1, 2, 3, and 4, and so on and so on. So notice how all my exponents is the first one is a 2, the second one is a 1, the second exponent is a 3, and the last one, there's no exponent or the exponent is 0. So this makes it a polynomial function because all the exponents are whole numbers. Now how do you write it in standard form? Well, you have to put it in, I'm going to go ahead and move this so you can have space. We have to put this in decreasing order of the exponents in order for us to write it down in the standard form. So the standard form would be f of x equals 5x to the third plus x squared minus 3x minus 2. So if the exponents are in decreasing order of the exponents, that means that function is in standard form. The leading coefficient is the number in front of the x with the highest exponent. The degree is the biggest exponent, and the type is based on the degree. Because the degree is 3, we call this a cubic function. The constant term is a term that has no x's attached to, so it's a -2. So this is a little review from what we did in first part of this section on how to graph polynomial functions. Please stop the video and write this on your notes at your own pace, but make sure you have it on your notes. So today's lesson is going to be about how to graph them actually. So we're going to start off by saying, polynomial functions are functions, or the graph of polynomial functions are always very smooth, and they're always connected. They are what we call it in mathematics continuous. That means there's no gaps, there's no breaks, there's no holes in them. It's just a continuous and smooth graph. So keep that in mind. You're going to need that when you get into a calculus class. But let's go ahead and talk about end behavior. It turns out all polynomial functions have something in common, or I should say they have some predictable behavior as we go to the right and as we go to the left. So that's what we call end behavior. To think about it, you might want to ask the question, how does the graph look or behave as x goes to positive infinity or negative infinity? So the only thing that we have to really focus on and what determines whether the function or how the function behaves is basically these two important parts, which is we call the leading coefficient and the degree. Those two things we're going to use to figure out what the end behavior of a graph is. If you have a function that has an odd degree and a positive leading coefficient, it turns out the behavior as you go to the left is always going to be going down like this, and as you go to the right is going to go up to infinity like this. So we call this the end behavior. We don't know exactly what happens in the middle. We know that the end behavior is like that. So I like to make my middle part dotted so that I know that this refers to the end behavior, not necessarily to what happens in the middle. Now we use symbols to explain what's happening. We say that f of x goes to infinity as x goes to infinity. In other words, as you move to the right, the function, the graph goes up to infinity. That's what this statement would be saying right here. And so on the other one, it says f of x, or the graph of f of x, goes down to negative infinity as x goes to negative infinity. In other words, as x moves to the left, the graph is going down to negative infinity. So similarly, for an even degree and a positive leading coefficient, the graph is always going to look like this. It's always going to go up this way and it's going to go up this way. In the middle, they could do many, many, many things. Something that is not so predictable. But for the end behavior, both parts of the graph are going to approach infinity as x goes to negative infinity and as x goes to positive infinity. Now please remember that if you change the leading coefficient, if you multiply it, it's a reflection over the x-axis. So that means this graph for an odd degree and a negative leading coefficient is going to go up to infinity as you move to the left, and it's going to go down to infinity as you go to the right. So something like this. And so a reflection of the next graph would look something like this. It's going to go down to infinity as x goes down to infinity, and f of x is going to go down to infinity as well as x goes to positive infinity. Again, the middle is not so predictable, so we draw it with dotted curve. Here is a nice organizer on how n behavior looks like based on the degree and based on the sign of the leading coefficient. Please write this down in your notes and use it wisely to do examples like we're about to do. So to graph a polynomial function, we're going to follow two easy steps. We're going to find a few points on the graph, like we did on the last lesson, and then we're going to use n behavior to connect the points with a smooth and continuous curve. So let's take a look at example 1 right here. The first thing we have to do is find a few points on the graph. Let's go ahead and start by writing this function in standard form. In standard form, this f of x is equal to 3x to the fifth plus x squared minus x. And the first thing I want to do is I want to find out a few points. Don't find too many, but you don't want to use just 1 or 2. You have to find somewhere between 3 and 5 points. So what happens when x equals negative 2? Negative 1, 0, 1, and 2. When x equals negative 2, this is going to give us negative 32 times 3, which is negative 96, plus 4 plus 2. This is going to give us a negative 90. When x equals negative 1, I'm just going to do it mentally because I don't have the time to show all the work. But maybe I might as well just do 1. I'm substituting into the different formulas, but it's okay. Negative 1, that's 1, negative 3, and positive 1. So this is negative 1. When x equals 0, it's easy to see that the function is going to give us 0. When x is equal to 1, it's going to give us 3. Check the work, please. And when x is equal to 2, we get a total of 96. Check those numbers for me, please, and then we'll do that. So here, so the first part is done. We found a few points and we could go ahead and actually plot them. But the next part is we need to take a look at the n behavior. What does the n behavior of this graph look like? First of all, the degree, we really don't care about the degree, whether the degree, what the degree is, but we do care about whether it's odd or even. So this degree is 5, that means it's odd. And then the leading coefficient is 3, which is positive. So looking back at the previous chart that we drew, because the degree is odd and the leading coefficient is positive, that means this is the kind of behavior that we're going to be expecting to see on that graph. So we know that the behavior is this way. So something like that. And so let's go ahead and plot some of the points. I know we're not going to make, or we're not going to draw 90 and 96, but let's draw these 3 here, or let's plot those points. Negative 1 is here, 0, 0 is here, and then 1 and 3. And as expected, because we knew this is the kind of behavior that we're getting, we're going to connect this graph with a smooth curve, and that graph is behaving that way as we go to the right. It turns out this graph actually does something like this, but this is a pretty accurate graph of that function here. Please pause this video and rewind it if you need it, so that you could see and hear how we get to do this. Okay, so copy this example on your notes on how to graph a polynomial function. Let's take a look at the next one and the last one here. If we have h of x equals negative x to the fourth plus 3x squared minus 2x minus 2, we're going to start off again by finding a few points on that graph. The more you do, the better, but we don't have the time to do 20 of them, for example. So let's just do about 5 of them. Negative 2. Be careful with this order of operations. I don't know what happened here, but here we go. Be careful with the order of operations here. Negative 2 to the fourth. If you do this carefully, this is going to be negative 16 plus 12 plus 4 minus 2. And so I believe that the answer here is negative 2. I run out of space. Negative 2. So we have a point, negative 2, negative 2. When x equals 1, I'm just going to do it mentally negative 1 mentally really quick. We get negative 1, 3, positive 2, and negative 2. So the answer is 2. When x equals 0, it's easy to tell that the answer is negative 2. When x equals 1, we get negative 1 plus 3 minus 2 minus 2. So the answer is negative 2. And finally, when x equals 2, we get negative 16 plus 12 minus 4 minus 2. So that'll be a total of negative 10. Okay, plotting these points, if you want me to plot these points, I'll write that negative 2 here. Plotting these points, negative 2 is about here. Negative 1, 2 is about here. 0, negative 2 is here. 1, 2 is here. And then 2, negative 10, so obviously going to be down there somewhere. Okay, so these are the points. Now, how do we describe the end behavior? Again, what is the degree? And what is the leading coefficient? The degree in this one is 4, and the leading coefficient is negative 1. So obviously this is even and negative. So when we look at the chart, we see that for an even degree and a negative leading coefficient, this is what the end behavior is going to look like. And so we know for sure that this behavior is going to go like this, like that, and it's going to do something crazy like this. So from this point then we could go ahead and say that the graph is going to look like, I'm just trying to pick a different color, but I'll just do it like this. This graph is most likely going to go like this, approaching negative infinity. Here is going to do something crazy, like we did notice. It actually does something like that. And you can go to desmos.com and type this in. You're going to see that my graph and the graph that Desmos will produce are very, very, very close to each other. Please review this, find more examples on the internet, and then make sure you understand everything. Have a wonderful day.